Hello everyone, my name is Gus Smith, and today I'm going to talk to you about work I did with my colleagues at the University of Washington titled Pure Tensor Program Rewriting via Access Patterns. Imagine we have a hardware designer who has designed a hardware accelerator for machine learning, a matrix multiplication unit called a systolic array. She can describe very precisely how it functions. For example, she might tell us, it reads an entire weight array of shape rows by calls, it then pushes n vectors of length rows through the array, it computes the dot product of every vector with every column of the weights, and finally it writes out n vectors of length calls. Yet despite knowing all of this, she might still have no idea how to compile for her hardware. To compile for custom hardware, hardware designers need to either build their own compiler or build a new backend into an existing compiler. In the deep learning sphere, TVM and PyTorch are popular choices. Yet both of these approaches are challenging even for compiler engineers. But given how much detail we have about how the hardware functions, could a compiler use that information to map to the hardware automatically? That is, could we compile her description of the hardware into a pattern, which could then be used to search through the workload in question and automatically insert calls to her hardware? We posit that this is possible. We posit that hardware mapping is a program rewriting problem. But if we're going to tackle hardware mapping as a program rewriting problem, then we need the right intermediate representation, and current IRs are not up to the task. We have three requirements for an IR used for hardware mapping. First, the language must be pure, which enables the equational reasoning required for term rewriting. Second, the language must be low level, so that we can actually reason about the hardware. And lastly, the language should avoid binding, which makes term rewriting much easier. Binding structures, such as lambdas, provide expressiveness. However, they are difficult to deal with in term rewriting. For example, rewrites must explicitly ensure that they do not introduce name conflicts. Thus, we seek to avoid using binding altogether. To survey the landscape of IRs we could potentially use for hardware mapping via term rewriting, let's look at three examples of IRs within the deep learning compiler TVM. TVM's highest level language is Relay, which is pure and allows us to avoid binding. However, Relay is not low level. What makes Relay high level is the fact that, in Relay, key kernels such as 2D convolution and matrix multiplication are opaque. That is, their underlying implementations are not expressible in Relay. To describe the implementations of these kernels, TVM uses its lower level IRs TE and TIR. While both of these IRs are appropriately low level for hardware mapping purposes, they both rely heavily on binding constructs, in addition to the fact that TIR is not pure. And while we are only talking about TVM here, the same shortcomings are present in the IRs for other modern frameworks. In short, current tensor IRs fall short on our requirements. Thus, in this talk, we present a solution. We first present our core abstraction, access patterns. Around them, we design Glenside, a pure, low-level, binder-free IR. Finally, we demonstrate how Glenside enables low-level program rewriting, including hardware mapping. The rest of this talk is structured as follows. First, we will attempt to implement matrix multiplication in a pure, low-level, binder-free way. We will then use what we learned from that experience to define access patterns in the Glenside IR. Finally, we will go through some case studies showing the utility of access patterns in the Glenside IR. So let's begin with matrix multiplication. Remember, our goals are to represent matrix multiplication in a way that is pure, is low level, and avoids binding. Just to remind ourselves, here's the matrix multiplication algorithm. Given matrices A and B, pair each row of A with each column of B, compute their dot products, and arrange the results back into a matrix. This simple English description of the algorithm immediately suggests a possible pure, low-level, binder-free implementation. First, we view the matrix A on the left as a list of its rows, and the matrix B on the right as a list of its columns. We then pair each row from A with each column from B by taking the Cartesian product of the two lists. The result is a list of row-column pairs. Finally, we map the dot product operator over this list of row-column pairs. Our result is a list of scalar values. But there's a problem. A 2D matrix times a 2D matrix should produce a 2D matrix. However, our algorithm produces a one-dimensional list of values. Even if the values are correct, we're missing a core piece of information, the shape. Let's step back in time to understand where the shape information got lost. By the time we're mapping the dot product operator over our list, the list is already a flat list of pairs, as is the case in the step before. But at this step, just before we take the Cartesian product, all of the original shape information seems to be present. Specifically, we still have A and B in their two-dimensional forms, as a list of rows and columns respectively. So shape information is present here, but when we step forward again, the shape information is lost. Our 2D matrices have been flattened into a one-dimensional list, with no way to recover the shapes of the original matrices. So it seems that the Cartesian product operator is destroying our shape information. Thus, we introduce a new two-dimensional Cartesian product operator. This new Cartesian product operator preserves shape information. Now the Cartesian product of the 3 rows of A and the 2 columns of B are a 3x2 matrix of pairs. But now, when we try to map our dot product operator over our new list, we run into another problem. Our map operator maps the dot product over the wrong dimension. Thus, we also introduce a new map operator. This map operator knows to map the dot product 2 dimensions deep, correctly mapping the dot product onto the row-column pairs. Finally, we get out what we expected, a 2-dimensional matrix with the shape information preserved. So what happened here? Cartesian product 2D and map 2D hard code which dimensions are iterated over and which dimensions are computed on. But if the shapes of A and B change, we'll need entirely new operators, for example, map 3D. So can we encode this information, that is, which dimensions are iterated over and which dimensions are computed on, directly in the tensor itself? Unsurprisingly, the answer is yes. This is exactly what access patterns do. Now we'll talk about the design of access patterns. Access patterns simply add a bit more information on top of a traditional tensor. Whereas a tensor is defined by a tuple of integers called a shape, in this case 3, 4, an access pattern is defined by a pair of tuples, where the first tuple holds the access dimensions, or the dimensions that are iterated over, and the second tuple holds the compute dimensions, or the dimensions which are computed on. Concatenating the pair of tuples gives the shape of the underlying tensor. An access pattern simply represents a view over a tensor, conveying how an algorithm computes over the tensor. For example, this access pattern is viewing our 3, 4 shaped tensor as a 3-length vector of 4-length vectors. But if we shift the dimensions of the access pattern over, we can view the same tensor as a 3, 4 shaped tensor of scalars. And if we shift the dimensions in the other direction, we can view the same tensor as a scalar-shaped tensor, in which the quote-unquote scalar, i.e. a single element, is a single 3, 4 shaped tensor. Thus, each of these different access patterns represents a different view on the same underlying tensor, each view being potentially useful depending on the algorithm processing the tensor. Now, once we've defined access patterns, we can redefine a bunch of common tensor and list operators using access pattern semantics. All of these operators collectively form the Glenside IR. There's a bunch of detail about the operators in the paper, and we'll see a few of them in our case studies. Now that we've defined our core abstraction, access patterns, we will demonstrate how access patterns in the Glenside IR enable rich term rewriting over tensor programs. We begin first by showing how Glenside cleanly represents 2 core deep learning kernels, matrix multiplication and 2D convolution. We then return to our original task, and show how Glenside can be used to implement hardware mapping via program rewriting. Finally, using equality saturation, a modern program rewriting framework, we demonstrate how Glenside can discover ways to flexibly map other kernels onto hardware that was designed for a specific purpose. In this case, mapping 2D convolution onto matrix multiplication hardware. Let's begin by re-implementing matrix multiplication with access patterns in the Glenside IR. Remember, we defined our matrix multiplication algorithm as, given matrices A and B, pair each row of A with each column from B, compute their dot products, and arrange the results back into a matrix. We will now implement matrix multiplication with Glenside. In these slides, the Glenside expression will appear on the left, and the access pattern shape of the Glenside expression on that line will appear as a Lisp-style comment on the right. To begin implementing matrix multiplication, we first need to access A as a list of its rows, and access B as a list of its columns. Accessing A as a list of its rows is straightforward. Given a tensor and a dimension index, the access operator converts a tensor into an access pattern by splitting the tensor's shape at the given dimension index. In this case, A is a 3, 4 shaped tensor, so accessing it at dimension 1 produces this access pattern shape. This access pattern views A as a 3-length vector of 4-length vectors. In other words, a list of the rows of A. Next, we must access B as a list of its columns. Accessing B at dimension 1, however, gives a list of B's rows. Thus, we employ transpose, which we call an access pattern transformer in Glenside. Given an access pattern and a list of integers, transpose reorders the dimensions of the access pattern. In this case, we simply swap the dimensions of the access pattern, giving us a 2-length vector of 4-length vectors, or a list of B's columns. Now that we have a list of A's rows and B's columns, we use Glenside's Cartesian product transformer to create every row-column pair. Notice that the resulting access pattern is a 3, 2 shaped matrix, each element of which is a 2, 4 shaped matrix. The 3, 2 shape preserves the shape information from A and B, and will give us the final shape of the output matrix. The 2, 4 shape represents a pair of 4-length vectors, one row of A paired with one column of B. Finally, we compute the dot product of each row-column pair. Glenside's compute expression maps a given operator over the compute dimensions of the access pattern, i.e. the second shape tuple, completely ignoring the access dimensions, i.e. the first shape tuple. In this case, the dot product operator reduces each pair of 4-length vectors into a scalar. And that is our full representation of matrix multiplication in Glenside. As you can see, our representation here is pure, low level, and conveniently avoids relying on binding. Next, we'll demonstrate the expressiveness of access patterns by implementing an entirely different kernel, 2D convolution, with Glenside. Let's first get a brief refresher on how 2D convolution works. The inputs to 2D convolution are a batch of image or activation tensors and a list of weight or filter tensors. In this example, we will show what happens with just one set of activations and one filter, as the same process is repeated for every set of activations and every filter. The filter is applied onto a window of the activations by computing an element-wise multiplication and sum between the filter and the window of activations. This element-wise multiplication and sum is computed over every possible window of the activations. This same process is completed for each filter in the set, producing one output channel for each filter. To implement 2D convolution in Glenside, we begin by accessing the weights as a list of 3-dimensional filters. In this case, there are O filters, where O will be our number of output dimensions, and each filter is of shape C, KH, KW, where C represents our number of input channels, and KH and KW are our filter height and width. Next, we access our activations as a batch of n 3-dimensional images, where n is our batch size, and H and W are the input height and width. Now we must form windows of our activations. As this is a common pattern, also appearing, for example, in max and average pooling, Glenside provides the windows transformer for this purpose. The windows transformer takes an access pattern, a window shape, and a list of strides. The result of the windows transformer is a new batch of images of shape H', W', where at each location in the new image, there is a C, KH, KW shaped window, representing each possible window of each image in the batch. Next, we use the Cartesian product transformer to pair every window of every image with every filter. Finally, we compute the dot product of each window-filter pair, which element-wise multiplies each 3D window with each 3D filter and sums the results into a single scalar value. This represents the core of the Glenside implementation of 2D convolution. Optionally, we can also remove and rearrange some dimensions so that the output layout matches the input layout. Now that we've shown that Glenside can represent common machine learning kernels, let's understand how it can be used for term rewriting. We begin by addressing our original goal. Recall our original idea, that hardware mapping is a program rewriting problem. Can we turn our hardware designer's description of her accelerator into a searchable pattern? With Glenside, we can. In Glenside, we can express our hardware as the following pattern, which matches a dot product mapped over the Cartesian product of two access patterns A0 and A1. Importantly, we can even express the fact that her hardware expects both access patterns to be vectors of vectors. We can then directly rewrite this pattern into hardware invocations, represented here as a new systolic array expression. We can even convey hardware parameters such as the number of systolic array rows and columns. Now we can use this rewrite to map our matrix multiplication to her systolic array. We have shown how we can use Glenside to formulate a program rewrite to perform hardware mapping. Yet mapping a matrix multiplication to matrix multiplication hardware is perhaps not all that impressive. To show the true power of program rewriting, with Glenside, we will now demonstrate the flexible mapping of a 2D convolution to matrix multiplication hardware. Looking at the Glenside implementation of 2D convolution on the left, and of matrix multiplication on the right, we can see a remarkably similar structure. Specifically, their core computation is the same. We take the Cartesian product of two access patterns and compute the dot product over the result. The primary difference is in how we form the input access patterns. Knowing that 2D convolution is so similar to matrix multiplication, it begs the question, can we apply our systolic array rewrite to 2D convolution? As it stands, the answer is no. The systolic array rewrite expects access patterns which are vectors of vectors, while the access patterns present in 2D convolution are much more complicated. However, if we could somehow flatten the access patterns to be vectors of vectors, we could apply our rewrite. So the question is, can we flatten our access patterns? The answer is yes, and it begins with a very simple rewrite. This rewrite matches any access pattern A, flattening and immediately reshaping A back to its original shape. On its surface, it may seem impractical that this rewrite is applied to every possible access pattern. However, using the equality saturation program rewriting framework provided by the EGG library, we can efficiently apply this rewrite in all possible locations and store all resulting programs. When we apply this rewrite, one of the resulting programs is the following. Notice the reshape and flatten transformers that have appeared on the two access patterns. However, our access pattern shapes haven't yet changed, as even though the access patterns are flattened, they are immediately reshaped back to their original shapes. To remedy this, we need to bubble the reshapes to the top. To do so, we can use these two rewrites, which express the composition commutativity of reshape with Cartesian product and with compute dot product. Note that these rewrites express general properties of glenside and are not specific to the task at hand. Once we apply these rewrites, our program looks like this. The reshapes have been moved out, and the access patterns are now flattened. We can now use our systolic array rewrite to map 2D convolution to matrix multiplication hardware. This transformation is not new. This is what's commonly referred to as the M2-call transformation for transforming 2D convolution into matrix multiplication. The remarkable thing is that with a set of 3 simple rewrites expressing general properties of glenside, we are able to completely rediscover the M2-call transformation. In conclusion, we have presented access patterns as a new tensor representation, we have used them to build the pure, low-level, binder-free IR glenside, and we have shown how they enable hardware-level tensor program rewriting. Glenside is an actively maintained, open-source Rust library public on GitHub. Please try it out and feel free to open any issues if you have any questions or encounter any bugs. Lastly, I'd like to thank everyone who worked on this project, my labs, and the funding agencies that made this work possible. Thank you for listening, and I'm excited to take your questions.